Hello everyone. In this video I'm going to show some examples of capacitor circuits, equivalent capacitance, how the charges are shared, how potential difference works, and so on, and especially some examples on RC circuits. We talk about how we charge a capacitor, like in here. If I connect my key to the left, the capacitor will charge, and if I connect my key to the right, then it will discharge through this resistor and make the system work. So this question is asking about that. We talked about how current starts from a value, what we call I0. If I plot current versus time, I'm going to see current dropping over the time, starting from a value of I0 and dropping exponentially. We talked about the time constant that is equal to R times C, and that shows me how fast the current drops, and the same goes for potential difference. It starts with a value of V0, delta V0, and drops and gets closer and closer to zero as the time passes. If we have a large tau or time constant, drop will be faster. Drop will be slower because it will take longer time for this tail to end up at zero. Large time constant, slower drop, and small time constant, faster drop. And we looked at a question of this sort here. We could draw actually graphs. We calculate time constants here to be 2 seconds here, for example. I'll compare only two to give you a better idea. And here we have 3 seconds. So if I plot current versus time for each of these, the smaller one will drop quicker and the larger one will drop slower. The same goes for potential. If I make it drop for potential difference versus time, they will be very similar. This question is a question asking about the time and how current changes over the time. So let's read it. The switch in the circuit has been in position A for a long time. That's the charging. Capacitor charges from the power source. So in a way we can call the left side here as charging side. It's fully charges, and then switch is changed to position B at t is equal to 0. When it says it fully charges, that means the capacitor gained a potential difference of 9 volt. I'm calling this potential difference at delta VC 0. At time 0, that's what it will have. That's what this 0 means here. What is the current in the circuit immediately after the switch is closed? That's the initial current, what we call I0. So it's asking me I0. What is that initial current? Immediately after switch is closed, we have this delta V0. We know our R in the system, the resistance. We can go ahead and apply Ohm's law to solve for that. And the other part of this question is asking what is the current in the circuit after 25 milliseconds. First of all, I can use again Ohm's law, apply to this. We've been using this already, so we're pretty familiar with it now. My initial current I0 is equal to delta VC 0 over R to get the initial current, and it will be 0.9 amperes. We have 10 ohm resistance, and we have 9 volt potential difference. To find the current at a time later, a time t later, and our time is 25 microseconds. Sorry, I think I said millisecond. Microsecond. Here is our equation, and we'll put in the values here. The current at any time T is equal to initial current I0 times e to the minus t, the time I'm looking for, divided by tau, which is the time constant or characteristic time. So once I input all these values, I'm going to get my result. And what I need here is the tau, which is calculated up here. It's simply the resistance in the circuit times the capacitance of the capacitor. And we calculate it as 10 microseconds using the given values of resistance and the capacitance. 10 microseconds. I know 25 microseconds later I'm looking for, and I can put in all the numbers and get it correct. That's how much we need to know about how the current is changing and potential difference is changing over the time as we discharge a capacitor, and how we can calculate those. Charging is slightly different. Current changes the same, but potential difference starts from 0 and increases to a value that approaches to the power source we put in the system. And here are the equations. There isn't much else to this. If I'm asked similar question, I can apply Ohm's law to find initial values, I0, delta V0, delta VC0 relation. And at any time, I can calculate current and potential difference using these equations. Notice the current calculation is the same, potential difference is slightly different. We won't be going into too much depth of this part, but the questions I'm solving here are what you want to focus on. This system here has a power source of 12 volt. First part is asking me what is the equivalent capacitance, C equivalent. That's one type of questions we might receive, we might want to focus on. This is a mixed capacitor circuit, so it's a complex capacitor circuit. We have 3 capacitors, these 2 are in parallel. Remember we read and reviewed that the parallel capacitors, their capacitances, I'm going to call this our C equivalent 1, we just add their capacitances. I'm going to name these guys for simplicity, so I can say this plus that. So C1, C2, C3, as you see, C equivalent 1 will be C2 plus C3. Parallel capacitor circuits works opposite to parallel resistors. So we just add them. 2 microfarad plus 1.5 microfarad, so 3.5 microfarad. That's the equivalent capacitance for this parallel part of my circuit. Then I'm going to simplify my circuit in a very similar way to what I did for the resistors. Whatever I worked on, I'll take those as one capacitance in my system, and whatever I didn't work on will stay as the same. So I have my C1 here already staying the same, not a resistance though, it's a capacitor. And C2, C3 I combined into one, C equivalent 1. And here's my circuit again. C equivalent 1 I found to be 3.5 microfarad. If I have the same units, I'm just adding them, I can stay in microfarad. And then I can change the farad when I need to later on. C1 is 4 microfarad. And clearly I have them in line, I will call along the line, they are combined and series. So this is in series, and that will give me my equivalent capacitance overall. C equivalent, now I say 1 over C1 plus 1 over C equivalent 1 to power minus 1, and I'll put in the numbers. 1 over 4 microfarad plus 1 over 3.5 microfarad to the power of -1. If I do this calculation, what I'm gonna get is my C equivalent will be 1.87 microfarad. That's 1.87 times 10 to -6 farad. I'll convert it when I need to. Again, I have only microfarads here and there. I can stay with the same unit. For part 2, how much charge flows through the battery as the capacitors are being charged, is asking me the charge. I'm going to find it in coulomb. This guy is in volts, so I'm going to convert my C equivalent to farad, 1.87 times 10 to -6 farad. And here I'll use Q is equal to C delta V, C equation in general. This is my general equation. Applying it to my circuit here, I'm walking back to my original circuit. I'll have a Q following here, Q total. Q pretty much works like current. This guy will combine, will accumulate some charges, and it will be the same as Q total. But as we get here, there will be divisions, so we will have accumulation of charges as Q2 and Q3 separated, and we will have Q1 equals to Q total. And as the same as a resistor circuit, parallel arms will have the same potential difference. Keep that in mind. We discussed this in the review for this lecture as well. Same potential difference or voltage. And the series arms shares the potentials from the overall power source. Of course, we don't need those for this one. All I'm asked to find is what is I total, Q total. Delete this part here. Okay. And I'll find it using this equation. It's the general form there, and I'm looking for this form of it. On my Q total will be equal to C equivalent I found times delta VC. That would be equal to epsilon. So total charge that my battery power supply provides to the system or flows through my power supply is 1.87 times 10 to -6 farad times 12 volt. SI unit, I'll get my Q total in SI unit, which will be coulomb. And once I do that calculation, I'm going to find 22.4 times 10 to -6 coulomb. Now I can change this, convert this to micro coulomb if I like. This is in micro 10 to -6, so I'll have 22.4 micro coulomb. I can also write it in that form. Please go ahead and think about how you would find Q2, Q3. Very similar to, again, resistor circuit. I know Q1, I can easily find potential difference across this first capacitor. I know Q, I know C, I can get to delta V using this general equation again, right? From this equation, I'll say delta V1 would be equal to Q1 over C1. And then whatever delta V, whatever potential is left will be shared by these two guys here. So I can find delta V2, delta V3, which will be the same, and then reach to the charges that accumulate on those capacitors. Please go ahead and practice on how to find those charges. I actually have the answers. If you do that, you will find them. Let me put them over here. Find Q1 and Q2 is equal to 12.8 microcoulomb, or that times 10 to minus 6 coulomb. Q3 equals 9.6 microcoulomb. And very similar to current, the charge on the first capacitor will be the same as Q total, which I already mentioned. It will be 22.4 microcoulomb. Let's list that as well. Alright, one more question and we'll be done with this video. For circuit below, what is the time constant? Tau. R times C. General form. This is my C here, but I have two resistors, so I'm going to find R equivalent, simplify it. Two parallel resistors are added in this way. I have 1 kilo ohm and 1 kilo ohm. Again, I'm gonna stay with the kilo ohm. I can convert to ohm later. It's all resistors, so it's not gonna cause me any trouble. 1 kilo ohm. I'll have 2 over 1, inverse it, I'll have 1 over 2 kilo ohm. So 0.5 kilo ohm is my R equivalent. And if I simplify, that's equal to 500 ohms. Then I can simplify my circuit to 1 capacitor, 1 resistor, RC circuit, right? C. And I'll have our equivalent here, 500 ohm. Whatever current was on this capacitor will be dissipated over this resistance. This is our equivalent resistance. It will generate a current when I close this, and then it will finish over the time. We will have an I total from here, and it will divide into 2. I1, I2. I would name these guys as well, R1, R2, and so on. But we're not looking into that. We're looking into what is the time constant. For the time constant, I'll use R equivalent. It will be C times R equivalent. My C is 4 microfarad, 4 times 10 to minus 6 farad. I'm going to find tau, the time constant, in seconds, so I'm converting everything to SI units. And my R equivalent is 500 ohms. That's equal to 2 times 10 to minus 3 second, or 2 millisecond. After I find that, if I'm given I total, that would be my I0. Initially starts as I0 actually. Doesn't always stay as I0, so let me change that. I0 is at current at T is equal to 0. If I'm given that, if I know the potential difference, I could calculate it using Ohm's law. I can find current at any moment in time using this equation, remember? And I can choose my T. I know tau, I know this guy. At any moment in time I can find the current. Current at time T. But it's not asked, right? It's not asked. If it was, I would be able to find it, given the values. The same goes for potential difference at any moment in time is delta Vc 0 e⁻ minus t over tau. That's how tau is useful for us. It helps us find current and potential difference or voltage at time t. Knowing the initial values of current and potential difference, or I0 and delta Vc0. Alright, hope this was helpful, and we'll do some more examples.